Good morning. In today's episode, we're going to be looking into how exactly we go about extracting metals from their ores. We'll look at the different methods, we'll look at why we use each different method, and we'll talk about the equations that go with them as well. This is What's Your Question? Let's go! For the starter then, I've placed for you 4 questions here that are: name 3 metal elements, name 3 non-metal elements, what does the atomic number tell you about an element, and what does the atomic mass tell you about an element. You should look those up in the periodic table and then define those 2 final ones for me. Can you pause the video here, either throw your answers down the questions, or have a think about and write it down somewhere? I'll give you the answers in a second. Okay, so any 3 metal elements, you'd be looking at anything that is to the left of the red line I've drawn on this periodic table. You can see here, you can name any of those elements and they are good examples of metals. Anything to the right of the line that I've placed here would count as good examples of non-metal elements. The atomic number for an element tells you the number of protons found inside the element. And if you ever ask to find out how many electrons there are, the number of electrons will be equal to the number of protons in any element, any atom with no charge at all. The atomic mass tells you the number of protons and neutrons inside of a substance. It also tells you the mass in grams of 1 mole of any given element that we have here. 3 objectives for you today. We're going to start off by being able to recall the reactivity series. We're going to describe how we can extract metals that are less reactive than carbon, and we're going to describe how we can explain how we can extract metals that are more reactive than carbon as well. Okay, so objective 1, the reactivity series. This is the reactivity series, starting with platinum, gold, silver, which are very unreactive elements. We can move up to look at copper and iron and substances like that are slightly more reactive, until we get to the very top of the table where we have some very reactive metals up there at the top. We don't really find many of these metals as pure elements, so if we want to use them, we need to find ways to extract them from compounds which they're made up of. All of these things can be found in the Earth's crust, and so we need to find ways of extracting those metals from those rocks. The best way for us to do that, or the best ways for us to do this, are outlined on the slide that you can see here. Now, those at the bottom of the reactivity series, those very unreactive metals like gold, silver and platinum, are generally not going to form compounds very easily. So when we find these, we generally find them as elements with dirt and impurities inside of them. So they're not compounds, they're elements. So all we've got to do is remove the impurities, and we do not need to do any special chemical reactions in order for that to happen. As we move up the table, this becomes slightly more difficult as these substances become more reactive. Everything leading up to carbon, so on the one you can see here, that's zinc, iron, tin, lead and copper. These substances we need to extract from an ore. Now, ores are the rocks we find in the Earth's crust which contain these metals. And they're either going to be carbonates, so calcium carbonate, copper carbonate, or they can in some cases be sulfates as well, so copper sulfate and things like that. There are many examples of ores we may find in the ground, and to extract those, we use a process called reduction. Reduction just means that we're going to break these carbonates down into, so they're oxide compounds. So for example, that calcium carbonate, we break down to calcium oxide. We'll talk about it in more detail in a second. And we'd extract it by reacting that substance with carbon. At the top of this table, the things above carbon, we can't do that with, because for carbon to remove those substances, carbon has to be more reactive than those elements. Carbon is not more reactive than aluminium, magnesium, calcium, sodium and potassium, so we cannot use that process with those top most reactive elements. With those, we use a process called electrolysis, which again we'll go through in more detail later in the lesson. As an example here, I'm going to work with copper carbonate. I'm going to talk through the process we follow to extract copper from copper carbonate. Whenever we're extracting a metal from a carbonate ore, the first thing we need to do is to turn it from a carbonate, so copper carbonate, we should turn it into an oxide. We can do this through a process called thermal decomposition. This just means that when we heat it, it will break down. I put the equation for this here, so we can see that when copper carbonate is heated, it forms copper oxide and carbon dioxide is released. We're then left with only copper oxide. There's nothing else in there but copper and oxygen. For the second step here, we need to extract the copper. Now, this works with carbon because carbon is more reactive than copper, and we're going to get what's called a displacement reaction. When I heat the copper oxide with carbon, the carbon is going to replace the copper in this compound because carbon is more reactive than copper. This would not work, again, with any element more reactive than carbon. It just doesn't work at all. I've placed here, you can see the word and symbol equations, and you can see that that copper oxide will react with the carbon, and the carbon will take the place of the copper, and the most stable version of the compound that can form is carbon dioxide. So that's what we end up seeing. I've also placed the balanced symbol equation for that as well, where you can see that copper oxide, which is a solid, which is what those little S's mean in the brackets, plus carbon will make copper and carbon dioxide as our product. The only thing we'd be left to do then would be to extract the copper and use it for whatever you want to use it for. This process would work with any of those metals in the middle of the reactivity series because they are all less reactive than carbon, and as long as you're using the ores, you'd have to follow similar steps to this. Some metals we need in particularly large amounts, and a good example of this is iron. Because we need it in such huge amounts, the method we use to extract it is a very large scale version of the reduction process I just talked about. When we're extracting iron in large amounts, we use something called a blast furnace. As I said before, we need to make sure it's as hot as possible, so we use the blast furnace, which is very, very hot, to make sure we are able to carry out the reduction reaction we talked about when it came to copper. Blast furnaces look like the one you can see in the image here. At the bottom of this, we have liquid iron coming out, and we also have something called liquid slag. We'll talk more about what that is in a second. The whole middle section you can see there is just a very hot section of the blast furnace where things can do the reactions they need to. And at the top of this furnace, we are going to feed in coke, which is just carbon. We're going to feed in limestone, which is there to remove some of the impurities in the iron ore that we're going to use, and the iron ore is also going to be fed in here as well. Iron ore is generally called ferrite, and this will be iron oxide with other impurities mixed in with it. That iron oxide is going to drop down into the hotter section of this blast furnace. It's going to be heated up to a very, very, very high temperature, so it effectively becomes a liquid. When this happens, that iron ore is going to start reacting with the carbon. It's going to do exactly like we said before with the copper. The carbon is going to replace the iron in the iron oxide and form carbon dioxide. And you can see at the top of the furnace, there's a space for waste gases to come out, and that's where the carbon dioxide would leave this blast furnace. Our products here then are going to be iron and carbon dioxide being given off, and those impurities are going to react with the limestone to make the substance called slag, which again, because it's so hot, will be a liquid. And you can see at the bottom the liquid slag comes off to one side, and the liquid iron, which is more dense, more heavy, will come off to the other side. I've placed just to the right of that a bit of a description of what each of those things does in more detail. The reactions that are happening inside here are on this slide that you can see. So the iron oxide is going to react with carbon monoxide, which is going to be produced. That carbon that we placed into there is going to react with the oxygen to make the oxygen that's being pumped in through the bottom of the blast furnace. It's going to react with that to make carbon dioxide, and the carbon will also, to make carbon monoxide, and then the carbon will reduce any carbon dioxide present to make it into carbon monoxide as well. So the carbon monoxide we're getting here is mixing, that is coming from a reaction with that carbon inside the blast furnace. So we're mixing carbon monoxide with iron oxide, and again, as I said, we're making iron and carbon dioxide in this. And I've placed the balanced symbol equation for you to see there also. The slag, as I said, is a reaction with those impurities in the iron ore, and that iron ore impurity is generally a substance called silica or silicon dioxide. And the substance we end up forming with this is called calcium silicate. And you can see that in the symbol equation and the word equation at the bottom of this slide. In this diagram, you can see the way we'd extract those most reactive elements in the reactivity series. These are all substances that would be more reactive than carbon, so we can't use the reduction process. Wherever possible, we would try to use the reduction process because it is significantly cheaper than this method that we're going to talk about next. But because we have no other option with these metals, we have to use electrolysis with these. Okay, when it comes to aluminium, which is the example I'm going to talk about today, we would set up our electrolysis system to look like this. You can see here there is a cathode and there is an anode. Now, because a circuit is involved here, these will be connected into the circuit, and one of them will be positive and one of them will be negative. You can use the acronym PANIC, P-A-N-I-C, to help you remember which one's positive and which one's negative, because the positive is the anode and negative is the cathode. So we can then use that acronym to remember which of these is which. You can see the outside casing of this container would be the cathode, so it would be the negatively charged electrode we'd be using electrolysis, and the ion attracted to this would generally be the positive ion, and our metals are always positive. In this case, because we're trying to extract aluminium, it's likely our aluminium is going to form next to our cathode here. The anode is our positive electrode, and that means that the negative ion will be attracted to it. Because we're working with an ore, aluminium or bauxite, the substance other than aluminium there will be oxygen, so oxygen is likely going to form at our anode. Because we need to pass electricity when it comes to electrolysis, because electrolysis is going to split our bauxite using electricity, and we can tell that because electrolysis literally means to split using electricity, because electro means electricity and lysis means to split in Latin, so we have electrolysis, to split using electricity. We need to have an ore that conducts electricity. Now, as a solid ore, the bauxite will not conduct electricity, so we have to either melt it, which would take a very high temperature and be very expensive, or dissolve it in a solvent. In this case, we use a substance called cryolite, and we dissolve our aluminium ore into the cryolite. So the browny orange substance you can see here would be a solution of bauxite, our aluminium ore dissolved in molten cryolite. We now have got a liquid which has got ions, because our ionic substances here will be able to move around, so they'd be conducting electricity. And for anything to conduct electricity, it must either be melted so that the ions can move, or dissolved in something so the ions can move. In this case, it's dissolved, so the ions are able to move around. So when we run electricity through this, the positive ion will be attracted to the cathode, and the negative ion will be attracted to the anode. And we can see here that the aluminium, the positive ion, is attracted to the bottom of this container, and the oxygen, the negative ion, is attracted to each of the different electrodes. We can extract the aluminium as we need to. There'll be little open feed tubes out the bottom of that container, so all the aluminium runs out, and the rest of it could then be reused. Those graphite anodes at the top that you can see would react with the air, because it's very hot when this happens, and that would mean that over time they'd make carbon dioxide and they would break down, so they would need to be reformed on a regular basis, and this process can also be expensive. So there's lots of extra steps here that you need to consider when it comes to making sure that this process is going to work effectively and as cheaply as possible. When we have reactions like this, electrolysis, we have something happening at each electrode, so we have reactions happening. We have what's called a reduction and an oxidation reaction happening. The reduction is where electrons are being gained, and the oxidation reactions are where electrons are being lost. For aluminium, it is gaining electrons. So of our reactions happening here, we can see that reduction is happening to the aluminium. We can see aluminium's gaining 3 electrons and making an aluminium atom. Half equations just describe this happening. So we can see we start with an aluminium ion, it's in group 3, so it's a 3+ ion. It gains 3 electrons, it becomes aluminium again. For oxygen, oxygen is going to be our negatively charged ion. Oxygen is going to need to lose electrons for it to become an atom again because it's got two too many, that's why it's 2 negative. So our oxygen would lose 2 electrons normally, but oxygen always forms a diatomic molecule. So we have 2 oxygen ions making O2, and 4 electrons would then have to be given off. Finally, we can put those two half equations together to show exactly what's happening with a full reaction. We can see our aluminium oxide will be pulled apart using electricity to make aluminium and oxygen. And I've balanced this here because we know that 3 oxygens isn't going to work because nothing will go into 3. So I've 2 oxygens will never fit into you will never be able to balance it properly. So I've got 2 moles of aluminium oxide, and then 4 aluminiums will match up to that and balance the number of aluminiums, and 3 lots of the oxygen molecule will balance the amount of oxygen, and that's how we can balance that simple equation. If you have any questions about any of this, or it doesn't make sense, throw your questions down in the comments and I'll happily go through them with you, but that is the extraction methods that you need to know about for your GCSEs in C6. Thanks very much for watching. Make sure you stay safe, stay alert, stay curious, and subscribe.